So thank you very much, everyone, for having me here, and thank you, Meg and Pete, for having a great introduction. So I'm going to be talking today about erosion patterns from turbidity currents within the Congo Canyon using repeat bathymetric surveys in 2019 and 2020. This has important implications in helping us understand the burial efficiency of carbon, how nutrients and pollutants such as plastics are transported to the deep sea, and how turbidity currents act as geohazards, as well as to mitigate the impacts of turbidity currents to essential telecommunication cables. Now, Pete and Meg have given us an excellent introduction, so I don't need to go into this too much. However, what I'd like to point out is here we have the full submarine system. I'll get my laser pointer. So here we have the full Congo submarine system. So here is box C with Angolan waters, and the black outline is the extent of our survey. And here in point B, we have the international waters, which is the Congo Channel, and the black outline is the extent of our survey. They make up 40% of the total Congo Canyon and Channel. So now, throughout this presentation, I'll be referring to filling and flushing events. Filling events, as Meg has kindly introduced, do not travel to the lobe. They're the most common type of turbidity current that we see within the Congo Canyon, and they are actively, there is an active filling event occurring 30% of the time throughout the year in the Congo Canyon. They work to redistribute sediment within the submarine canyon, and they also provide additional sediment to the canyon. Flushing events, however, which are the big flows that we've been talking about, are turbidity currents that travel down the entire length of the canyon and channel. They're picking up sediment on its path and then depositing the sediment on the lobe. They work to redistribute sediment and remove the sediment from the submarine canyon and channel. So just briefly again, we surveyed the area in 2019. There are multiple filling events, and then there was a large flushing event which broke 2 submarine cables, and then there's another large flushing event which broke another cable again after it had been repaired, and then there are more filling events afterwards, documented by the OBSs that Meg just presented on. And then we did another survey in September 2020, and it's the difference between these 2 surveys that I'll be talking about today. So just a little bit on my method. On the top here, we have the 2019 survey, and the bottom, we have the same area of seafloor in 2020. To calculate the volumes, we can subtract the 2019 survey from the 2020 survey to give us our difference map. The difference map outlined in C highlights the difference between the 2 surveys. Erosion is highlighted in different shades of red, whilst deposition is shown in blue. You will notice that there is no deposition within the resolution of this survey in this portion of the canyon. I've used these difference maps to categorize the erosion and deposition, and then we have outlined the erosion or different categories in ArcGIS, and been able to calculate the volume of additional or missing sediment within the area that's been outlined. This specific example shows a flank collapse with a volume of almost 8 million cubic meters of erosion. It's important to understand the uncertainties with this data. So the resolution in the Congo Canyon in Angolan waters is generally 5 meters, as seen here, with water depths of 1,500 to 2,000 meters. In the submarine channel, that's up to 5,000 meters water depth, we have a resolution of approximately 15 meters. Now here we have the Congo Canyon, which is the most proximal part of the survey that I showed you earlier. These are the water depth of 1,500 meters to 2,000 meters. The graph shows water depth of the Thalweg in 2019 versus 2020. In the center, you can see the total difference in depth between the 2019 and 2020 surveys. Everything below 0 in red is erosion. Everything above 0 in blue is deposition. The black line on this graph represents the gradient of the Thalweg at that point. I've tried to match up with these dotted lines whereabouts on the plan view of the canyon you're seeing. So what's striking is the difference in this difference map is the sheer amount of erosion that we're seeing throughout the system. There's on average 10 meters of erosion throughout the entire channel floor of the Congo Canyon. The second striking observation is in this dip here. So this bottom one is just the depth of the Thalweg across the canyon. And we have this large knickpoint located here, which is believed to be, well, is an ancient landslide dam. Work by Ed Pope has documented this. So this is data from roughly in 2000, and then this is our 2019 survey. And what we can see is that there's been a large amount of erosion that's blocked the landslide dam and then allowed a lot of sediment to back up behind this region, upwards of 100 meters of deposition behind this dam. So what we can see is that this landslide dam here hasn't been entirely flattened by the by erosion, but has instead the knickpoint has migrated slightly up into this backup of sediment. So it's only been dented. So there's still a huge amount of sediment backed up here. The gradients that we're getting in the Congo Canyon, so between M3 and M4, which is our mooring locations, we've got about 0.3 degrees, and then about 0.57 across here, and then 0.32 along here, and 0.17 along here. So these are really small, really small gradients that we're talking about. And then we go to the international waters, so the most distal part of the Congo Canyon and Channel. The next few slides will be the eastern part, the middle part, and the western part of this channel, so that I can fit them all onto the slides. So in the eastern part, the most proximal of the channel, you can see up to 20 meters of erosion occurring immediately up channel of a very small knickpoint. The remaining erosion is small and predominantly outer bend erosion. If we go to the middle section, you can see that the majority of the erosion here is again due to an upwardly migrating knickpoint. But interestingly, there doesn't appear to be any migration of the knickpoints located further down the channel. So here we have a knickpoint that's roughly the same size, yet there's no erosion whatsoever. And here again, there is some erosion, but nothing on the scale of this knickpoint here. And then when we go to the most western part, so the very end of the Congo Channel, there's almost no erosion and deposition seen on the volumes that you're seeing in the previous slides. So something's happening here where we're no longer getting the amount of erosion and deposition that we see previously. So here we have the total change in volumes of sediment on the canyon and channel floor categorized into types. These types are knickpoint migration, outer bend erosion, channel floor only erosion, which is not including knickpoints, and then the total amounts of channel floor erosion, which is the sum of all the above. And then we have flank collapses. We can see here that the erosion vastly outweighs the amount of deposition. The reaches of the survey comprise of 40% of the total canyon channel length, so the total amount of eroded seafloor sediment may be around 2.7 kilometers cubed. This is a globally significant volume and is comparable to 1,300 to 2,700 megatons of seabed sediment, or 19 to 37% of the present-day annual suspended sediment flux from the world's rivers into the oceans. So we really are talking about vast volumes of sediment. So when I talk about the specific categories, we have channel floor only erosion, which accounts for about 63% of all the erosion in the canyon and channel. This doesn't have knickpoints at its head. These erosive features span the entire width of the canyon and channel floor, and they appear to be influenced very little by canyon morphology or hydraulic geometry, yet present a significant portion of the erosion. Outer bend erosion represents 6% of all the erosion seen. There isn't much erosion on the outer bends compared to the channel floor. It does, however, occur more commonly in the Congo Channel than it does in the Congo Canyon. Knickpoint migration represents roughly 25% of the erosion seen. Here we have two examples of knickpoints, one in the Congo Canyon and one in the Congo Channel. The relationships between knickpoints and erosion is very complicated. We don't have as frequent enough time lapse to tell whether or not this 2019 survey, the knickpoint here, extended all the way across to this location here, or whether or not this knickpoint extended and then died out, and then a new one was perhaps formed. But what we do know is that the knickpoints represent 25% of the total migration, and there are very complex patterns of migration. And then flank collapse represents roughly 6% of the total amount of erosion seen in the Congo Canyon. Above the landslide dam I mentioned earlier, you specifically have these cauliflower-shaped flank collapses, which appear to be associated with an undercutting of the channel floor below. And then below the landslide dam, you have less frequent and smaller landslide flank collapses. None of the flank collapses have any deposition associated with them, as presumably they would have been removed almost immediately by these turbidity currents. And this, crucially, there is also areas where there is no erosion.
2 minutes.
Brilliant, thank you. These areas appear to be generally in low points from the canyon, and it's important to understand exactly how and why these areas occur, because these will be the safest places to put submarine cables in the future. And then deposition. There isn't much deposition compared to the amount of erosion in the canyon and the channel. Deposition comes to about 33 million cubic meters. It's found almost exclusively on the canyon terraces. However, in the Congo Channel, where the resolution is about 15 meters, we probably don't have the resolution to actually see the deposition, as there's highly likely that there's more deposition in a thin layer throughout the entire system at a thickness that's less than our resolution. So to summarize, channel floor is the predominant form of erosion. Flushing events may be able to generate knickpoints and remove knickpoints. Flushing events cause knickpoints to migrate faster than previously documented. The flushing events have removed over 1 kilometer cubed of sediment throughout the surveyed area. Scaling this up to the whole system suggests 2.7 kilometers cubed of sediment that's been flushed out of the canyon onto the lobe. Not only is this a remarkable amount of sediment, but it explains how carbon can be transported very efficiently hundreds of kilometers from river mouths and continental shelves to the deep sea, creating unique ecosystems and creating a carbon sink. Here we analyze the erosion. We observe that it's not evenly distributed. The information will allow us to mitigate the potential for turbidity currents to break submarine cables, which could be very costly and damaging occurrence to cable companies and local economies that rely on fast information for trade and finance. Thank you very much.
Thank you very much for presenting this fantastic data, Sean. So is there a question coming in? There is a question coming in from Gabi Gutierrez saying, thanks for the talk. What parameters do you use to correlate knickpoints and conclude that they migrated from one survey to the next?
Most of the knickpoints we can see quite clearly are only a few kilometers upstream from a knickpoint that was seen in 2019. So we can see them in 2019, and then in the 2020 survey, normally we can quite clearly see the erosion that's occurred between one knickpoint and the next. The knickpoint that I showed you from Angola, which was a very complicated knickpoint, there appears to be an absence of erosion along this point, which is why we think that maybe this isn't the same knickpoint and maybe one died out and another one occurred, but it's quite complicated. However, if you look at the international waters, you can clearly see, so there will have been a knickpoint here, and then there's all of this erosion that's occurred, and then the erosion stops, and you can see a dip in the bathymetry where the knickpoint head is. So I don't know if that answers your question, but that's where we've decided the knickpoints are and where we've decided like they're associated with each other.
Yeah, so there's some expert judgment involved in it as well. Very briefly, while we switch over, question by Michael Sweet. I'm surprised that you don't see deposition on the channel levees. Any comments on why not? This might relate to resolution as well, I guess.
I think it does relate to resolution. So in Angola on the levees, you'd have to have deposition of more than 5 meters in order to actually see it really, which is going to be a lot of deposition if you're applying a thin or at least a 5 meter layer evenly across the entire system. And the same we then go in the channel, it has to be at least 15 meters for us to really pick it out. So I think there is deposition there, but I think it's purely just less than resolution because we are dealing with really deep water here.
Thank you very much, Sean, for your
you.
presentation and answers.